Good evening, Dr. Rao. Can you hear us?
Yeah, I'm back. Can you hear me?
Yes, you're
Yeah,
perfect.
now it's fine, sir.
Hi, Prasad. How are you? Hello, Dr. Prasad.
Dr. Rao?
Yes,
Sir, good morning. Very good morning, sir.
good to see you. Good to
Thank
hear
you,
you
sir.
now.
Thank you, sir. Thank you, and nice to hear you, and nice to see you again. And I was just telling Chenmay and Karthikeyan that Dr. Sudhakar Rao is a great inspiration for me, at least, and to talk on antennas, even though I'm not an antenna expert, he has been inspiring me for 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 working on this area, and taking for this area further for myself and my aircrafts.
No, you
So
are
I
too,
am
too
really
modest. You are
I'm
too
really
modest. I think you have done a lot of work, but
thankful, sir.
I am not modest, I am very honest that Dr. Rao is omnipresent like them signal.
Dr. Prasad might have told you different thing. Now he's telling different thing.
Yeah. Maybe let us start the proceedings formally.
Yeah, I think we'll start. Yes.
Yeah, so I'll just take a minute. So, welcome all of you on the third technical session of ISAW 2020, which is
Yeah.
a focused event focusing on industrial and space antennas. We are really happy to have the speaker, Dr. Prasad, with us today. I will not take much time because Dr. S.S. Kartikan from NIT Trichy, who is also an accomplished researcher himself, is going to chair this particular session. And just for the sake of information, I would like to inform you that all our speakers will be present at 8 p.m. for a panel discussion where Professor Yahya Antar, President-elect, Dr. Poddar, IEEE Chapter Chair Activity, and Dr. Siddiqui, IEEE Region 10 Coordinator, will also be joining along with the speakers, and myself will be coordinating and moderating that talk. So without taking much time, I hand over the podium to Dr. Kartikan to take over and chair the session. Thank you.
Yeah, thank you, Dr. Chinmayi. I am welcoming everyone for the second day of IEEE workshop on advanced antenna for space and industrial application. Everyone enjoyed the yesterday's session. Yesterday's session was full of technical content. Hope everyone enjoyed. The same way, today morning session also, we are going to have a eminent speaker, Dr. NNSRK Prasad with us. He is going to talk about advanced airborne antennas for fighter aircraft, and followed by Dr. Shivnarayanan in the morning session. And also we have two more lectures in the evening session also. I request everyone to participate in this workshop, and also please join with us for the panel discussion at 8 o'clock. I know Dr. NSRK Prasad for past 4 years, and we had many places, but it is formally introduced. Dr. Prasad has more than 32 years of experience in research, design, and development. Presently, he is working as scientist Hutch, outstanding scientist in Aeronautical Development Agency, India. He is currently the project director of LCA AFMK-1A program and associate technology director of Avionics and Weapon System Directorate. He joined ADA in 1998 from Samir, Mumbai, where he worked during 1986 to 1998. Dr. Prasad obtained PhD in Communication Engineering from IIT Bombay in 2003, MTech in Controls and Instrumentation, and BTech in Electronics and Communication Engineering from JNTU College of Engineering, Kakinada in 1987 and 85 respectively. He worked and contributed for the prestigious and very important national projects like MST radar for atmosphere research of ISRO, optoelectronic integrated circuit project for Ministry of Information Technology, RF networking of Indian Lighthouse and radio beacon projects of Ministry of Service Transport, active seeker project of DRDO, etc. during his tenure at Samir, Mumbai. Currently, he is working for another prestigious project of the nation, Tejas Indian Light Combat Aircraft project. Its variants for Indian Air Force and Indian Navy. He is also working for medium weight fighter and advanced medium combat aircraft and other projects of ADA. He has more than 100 publications in national and international conferences and journal. He is a senior member of IEEE USA, fellow of IETE, IE, OSI, VEDA, life member of ISOI, SEMCI, ASCI, ISSE, and CSI, and member of IET UK, AOC USA. Dr. Prasad was awarded DRDO Scientist of the Year in 2015. He guided independently many undergraduate and postgraduate projects. Under his guidance, 4 PhD programs completed for VTU, Belgaum, Karnataka, and one for MIT Chennai, Tamil Nadu. He has been a reviewer for journals of AESI India, IEEE, and IEE UK. So now I welcome Dr. N.S. Karke Prasad to deliver his lecture. One request for the participant, you can post your questions through the chat box. At the end of the session, it will be answered by the speaker. So thank you. Over to Prasad.
Thank you, Dr. Karthikeyan, for your, a nice introduction and inauguration of the today's session. And very good morning to Dr. Sudhakar Rao Garu and all of you on this session. And now I will start my talk. I am going to share my presentation now. Just bear with me a couple of minutes. Are you able to see my presentation now?
No, sir.
Not yet. Okay.
Okay, sir. Yeah. Yeah. Now we are able to see, sir.
Okay.
Now we are able to see your screen. Please open your PPT, sir.
Okay. You're able to see my PPT now?
Yes, sir. Yes, sir. Yes, sir. We are able to see.
Okay, I'm making it now. Right. Is that fine?
Yeah,
okay.
Fine, sir. Fine.
Okay. Okay. Let's start the session. So, very good morning. I would like to talk on the. See, I am basically working for Indian Light Combat Aircrafts, and as an aircraft, of course, they have a lot of RF and micro systems, and obviously, supported by the antennas. So we'll talk about the design and development aspects of those antennas, because unlike the antennas for the ground-based systems, the antennas for the airborne systems have certain special requirements, constrained requirements, and we have to design and develop the antennas to meet those requirements, to put it on the aircraft and make the system work. So those things we will talk about. Also, we have issues of in qualifying these antennas, certifying these antennas for the airborne systems like the fighter aircrafts, and again flight testing the antennas, in the sense that flight testing those systems for which these antennas are installed on the aircraft. So all these are a gamut of things which we'll just discuss in this session. And why I said advanced airborne antennas is that now we are moving from one level of aircraft design to the next level of aircraft designs, including some stealth features and things like that. And when we go for a stealth aircraft design, again, these antennas are going to play a role in the design. I will talk about that. Okay, so we have the kind of challenges, and obviously, when there is a challenge, there is an opportunity. Just associate with that, and if we take the challenge as an opportunity, obviously we can progress further. So uh, I'm able to change my slide. Okay, right?
Yes, sir.
You're able to see the change of slide. Okay. So
Yes, sir.
because I'm talking about fighter aircrafts, I should obviously say what is a fighter aircraft. I mean, not everybody is familiar with the fighter aircraft subject. So that's why I just put the very general kind of description of a fighter aircraft. A military aircraft is basically designed primarily it is for air-to-air combat against the other aircrafts. Because it's called fighter aircraft because it is not like bombers and attack aircrafts. So fighter aircrafts definitely need to have the kind of features like speed and maneuverability, and of course the small size relative to other bigger aircrafts, because fighter aircrafts need to move at higher speeds like 1 Mach, 2 Mach, and like that. And also the other one is maneuverability. The great characteristic feature is maneuverability at these high speeds. So that's how the fighter aircrafts are. And why we need to have fighter aircrafts? Of course, we have bombers and other combat aircrafts, but what is the real reason to have fighter aircrafts is the lethality of the fighter aircrafts gives the kind of edge for fighting. And when I have lethality means the kind of weapons and sensors. And obviously, when I have the capabilities, I need to survive in that fighting space, and then impinge the lethality on the enemies. So basically, to have lethality on the fighters, we have various weapon systems. Supported by the sensors like beyond visual range attack systems, close combat attack systems, and air to surface attack systems, joint attack systems, multiple weapon engagement systems, and all these are supported by the sensors like radar and other EW systems. So this is how a fighter has to be, and it is defined like that. So fine. Now coming back to our topic of these antennas. Why the antennas? Are a topic to be talked about for the fighter aircrafts is on the fighter aircrafts we have other systems in addition to the sensors like survivability suit we call it, which is like a navigation suit, communication suit, and the other sensor suits. The navigation suit will have various systems like GPS and VOR ILS systems. OmniRange and ILS instrument landing systems, and tactical navigation systems, and radio altimeters. So the navigation suit, obviously, those systems. And then communication suit has got radios. Now presently, of course, we are going for SDR and data links in the various bands, L band and X band, and of course other bands. And then sensor suits like radar and lightning pod and EW and identification systems we are associated with that. So all these systems, and being the RF and microwave systems, they have the antennas. So obviously we need to talk about antennas. So that's how our topic today. So obviously the stability. Of course, I'm talking about stealth aircrafts. So as I told you, antennas pose a special requirement when I go for a stealth design. that is radar cross section from the detectability point of view. And there the antennas play important role because the antennas generally we keep it on the periphery of the aircraft like spine or the fin or the wings. But they obviously being metal parts, they contribute to the RCS of the aircraft. So when I go for stealth design of the aircraft, obviously my RCS has to be low. So what do you do with these antennas which are projecting from the skin of the aircraft? So I need to make them confined or conformal so that my RCS contribution due to the antennas is at its lowest level. So that's where the important role antenna design play important role stealth aircrafts, and that's how to reduce the RCS of the aircrafts. We go for conformal antennas or concealed if conformal is not possible. So at least we go for concealed antennas. Also, of course, we can talk about other materials, like radar absorbing, structures and radar absorbing paints, which we put on certain, structures. And of course, the being the antenna, when I'm talking about antenna, I need to talk about radomes also, especially for stealth aircrafts. These radomes play important role for antenna also because to reduce the RCA signature, we need to go for frequency selective radomes surfaces so that in other bands, except the band where the system is operational, I can minimize the the RCS by partly absorbing or partly deflecting the radiation from the outside sources. So that's how FSS radomes also play important role, and the technology is the really challenging technology. So now coming to the point, the radar systems, EW systems, and CNI, that is communication, navigation, and identification systems, that is basically part of navigation and communication suite. So these are the systems on the and if you look at the LCA, which is very first aircraft of combat aircraft of our country. So this is how it looks like, and I'll show you the antennas on the. Of course, this is the next level of design of the combat aircraft, which we call advanced medium combat aircraft, which is a stealth aircraft designed for stealth air combat and combat air patrol, BVR combat, etc. And that is in air-to-air mode and air-to-ground modes and air-to-sea modes also. The aircraft is designed for performing various operations, combat. So if you look at this typical antenna installation on a fighter aircraft, you see there are a lot of antennas. As I told you, a lot of systems are there. Communication systems and navigation systems, identification systems, sensors like radar and EW, jammers, etc. So all these systems need antennas. So where do we put these antennas? Obviously on the aircraft at various places. You see the spine, depending on the system's location. We put some of the antennas on the around the nose cone in front of the cockpit, and then obviously in the belly side. So then some antennas on the fin, some antennas on the wings. So, but so far the conventional antenna design for all these systems in various bands calls for the kind of blade antennas, mostly the blade antennas, protruding antennas. These are all. So protruding antennas obviously gives a lot of drag for the aircraft, and so that is one of the major design parameters. I need to reduce the drag. So obviously these antennas cannot be, protruding, can be in bigger size. And so for that, generally what we do, we try to minimize the antenna size and see that the drag is and which will not affect the performance of the aircraft. So that is of it. Second part of it, the radar cross section (RCS) of the aircraft to make it minimal, especially in the stealth aircraft's design. So obviously the antennas cannot be protruding. So that's where we go for conformal designs of the antennas. So this is how the antennas now have special requirements for combat aircrafts. So need to be conformal with low profile, low drag, and obviously being the combat aircraft, we have stringent environmental requirements like the antennas has to withstand the kind of vibrations and shocks, and then high and low temperatures, etc. So obviously we have to qualify when we design and develop an antenna for these combat aircrafts of all these environmental requirements. And then other, because of the nature of sensors, we need wideband antennas for some of the sensors and omnidirectional antennas for some of the systems, and also multi-band antennas. And now, because I'll show you the number of antennas what we're having in a typical aircraft, there are something like 30-40 antennas. So 30-40 antennas, obviously the number is too high. Even make it conformal, still I have to struggle with this big number. And so why not we make it a shared aperture, so that one antenna can be an antenna can work for with wideband performance, can work for 2-3 systems. Panning across the bands. So if I have a wideband technology, so I can design antenna for, let's say, L band and S band, and make it conformal, and make it work for both the L band system and S band system, so that I can reduce the number of on the aircrafts. So that is where shared aperture concept comes in. So that is also another challenge for designing these antennas. So factors to be considered for antenna installation and fighter aircrafts. So we have to take care of the field of view of the antenna. That's where some of the antennas have to be omnidirectional, and some of the antennas have to be directional. So based on the system's requirements, and obviously the losses, because I have to keep systems somewhere on the aircraft, but antennas for good field of view, I may have to keep it somewhere else. For example, if the system is in the let's say in the middle of the aircraft, say near belly, and antenna for a good field of view, I have to keep it on the fin top. So obviously I have to run longer cables from the system to antenna on the back. So obviously the losses involved I need to take care of as per the system design and performance. And the third important factor to be considered is interference. Interference is, see, I have some 20-30 antennas on the aircraft close to each other in the frequency bands. Obviously interference is another issue which we face in many our systems, right? RF and microsystems. So I need to take care of those interference should not affect the systems. So how do I keep it? Of course, the first thing is which comes to our mind is keep enough distance between the antennas. Fine, but aircraft is not an infinite surface where I can keep antennas comfortably at a distance. Not possible. So there is very limited space available. So I need to keep antennas maybe next to each other. But interference I cannot tolerate. So this is how the design comes to design issues, installation issues on the aircraft become a very important factor to be considered. In fact, I will tell you what are the design steps we do when we start designing an antenna for an airborne system. So there are a lot of things which we need to consider before going to the real design. I will just come to that before. Okay, the other factor, drag, I already explained. The drag has to be kept to minimum so that antenna size cannot be bigger than certain size, and the physical features, like if it is conformal or concealed, that is the best thing. So we try to make it conformal or concealed, and then layout clearances we do. So basically, when I go for a design of the antenna for an airborne system, the first thing I ask is that where the antenna location, which is the location you are giving me. I ask the aircraft designer to start with the location where I have to keep my antenna. From that, the other things can start. So I ask first, okay, where are you? Which is the location you are giving me? So obviously, the aircraft design has got a lot of other constraints. aircraft, aerodynamic performance, things like that. So from that, I may need the best location, but be available all the times. So then whatever the location is given to me, I have to start with that and see that where I can put that antenna in that location. And then obviously, then which are the neighboring antennas for that antenna, and those antennas which in which the band they work, and how do I minimize the interference. So these are the issues first. So we start with the installation locations first, and see the how I can fit that antenna. And then only the antenna design starts actually. So we take initial kind of draft design and go and fit that design. That model into that particular installation location where it is given to me. And if that is comfortable, then only I go for other things. Another major factor for the design of the antennas on the aircraft is you don't get a comfortable ground plane on the aircraft, unlike the in other designs for the ground systems. Comfortable ground plane, I means the obviously you know that as a designers a good ground plane for antenna to work as an antenna. So for that, because the aircrafts now are increasingly becoming the composite, skin aircrafts. So because of other design reasons, we don't use metal on the aircrafts. We go for composite skins, composite airframes. So when the composite airframe, obviously I don't get very good ground plane. So obviously, so that is another thing which you have to look for. So the how to design the antenna with whatever the ground plane available to you, and make still it work and perform as we want. So some of the design considerations I have put it when we go for a design of these antennas for the aircrafts. So obviously the frequency of operation is one thing for which the system is designed, and the antenna has to be designed for that. And the impedance which we have to take care of, that is VSWR considerations, so that antenna will not have bad reflections and losses and all that. So radiation coverages like pattern, gain, beam width, side lobe levels, and the squint. Of course, these are the design parameters for any antenna, but because the aircraft has got certain requirements, so we need to carefully look at it. So these design parameters. Then of course polarization, or cross polarization discrimination, what is the requirement for the antenna design. Then the power handling, depending on the power which is available, which is required for the system. For example, radar, the powers are in kilowatts, and jammers, the powers are in kilowatts. Obviously, for other systems, may not be that high power. So I have to design the antennas for handling the power also. Then, and the nature of, because of the nature of the sensors, for example, EW sensors or EW systems require wideband antennas spanning from some 1 gigahertz to something like 18 GC. So that is where the wideband antenna requirements come. So these are the some of the design considerations for the antennas. And VSWR, obviously we keep something like good impedance 50 ohms. And for the transmitting antennas, we fall VSWR in the range of 1.5 is to 1 to less than 2 to 1 for medium bandwidth antennas, and VSWR less than 2.5 to 1 for broadband antennas. So these are the some standard design requirements. And for the receiving antennas, we follow something like less than 3 to 1 to 5 to 1. So that kind of typical numbers. And the radiation coverage, omnidirectional coverage for mostly monopole antennas of the blade shape, and broadband is achieved by flat radiating element of shapes like hexagon, oval, etc., printed or on dielectric boards. And gain, typical gain varies for these antennas minus 10 dBi to 2 dBi. Then the directional requirements like cavity backed antennas or Vivaldi dipole arrays we take, and gain varies between 5 dBi to 35 dBi. So these are the radiation coverage requirements. Then coming to polarization, most of the omnidirectional antennas are vertically polarized for our systems, and horizontal polarization used for certain systems like VHF omnidirectional range and ILS systems, and circular polarization used for the SATCOM and GPS and ESM systems. So that is the polarization requirements. Of course, design steps I just put it, but as I explained you so far, the design starts with the requirements of the location of the antenna and the space available and the ground plane available, and then the neighboring antennas, which are the neighboring antenna. All these are the things which we start with, then start the design of the antenna for the frequency band and other things like VSWR dimensions, and then of course the material consideration, optimizing the design. Okay, all these steps normally any designer follows for an antenna and other systems, but only I'm just emphasizing the issues for the combat aircrafts. So as I told you, we have communication, radiation and navigation antennas like in the bands like HF, VHF, UHF and L band, and a radar and EW in X band and broadband. Broadband EW things. So look at the antenna systems and requirements. As I told you, each system, how many antennas? Some of the systems require 2 antennas, top and bottom, and some systems like IF interrogator kind of things, they require 6 dipole antennas and things like that. So if I just take the stock of the antennas required for all these systems, communication, navigation, other sensor suits, something like 30 antennas, 40 antennas will come. Okay, if you take out all this. So that's how these 30-40 antennas, I have to keep it on the airframe of a small aircraft, like light combat aircraft kind of thing. So that is where the challenge. And this is where for the present new designs, the forthcoming designs of the aircrafts, we are looking heavily for a conformal technology for the antenna in all these bands and for all these systems. But obviously, you know that some of the systems, the conformal antennas may not be available. Conformal technologies may not be available. For example, EW systems, which are wideband systems, obviously high power systems like jammers, I may not be able to get the conformal antenna. So that kind of constraints are there. So we need to live with those constraints and move ahead. So the low RCS antenna design considerations, like for the stealth requirement, low observable antennas are required. So body conformal, body embedded, the antennas we go for, and shared aperture to minimize the number of antennas. And then obviously sometimes to reduce the RCS, we paint with RAM materials to reduce the RCS, and then impedance matching to absorb the incident radio waves. That is another way of active RCS reduction considerations. When the antennas have to be really, the impedance matching has to be achieved for reducing the RCS. That is another area of working for less RCS, consideration. Then shared aperture, of course, I told you how it works. Instead of designing each antenna for each system, I design one antenna with the broadband performance features, which can cater for at least 2 systems, so that each system in a time sharing method, they can share this antenna. That is one way. Or of course, the other way is space sharing also is possible. But that space sharing is just combining 2 antennas, one entity. But that in the real advantage. But time sharing can give me a greater advantage, so that the antenna is only one, so that I can minimize my other requirements like space and other things, so that one antenna I can use for 2 or more systems. So that's shared aperture concept also is very much important for the antennas for the stealth aircrafts. So just seeing that what are the parameters, conformity, shared aperture, and for shared aperture, of course, demands my systems also have to be integrated. Integrated RF systems I need to design. For example, single transmitter wideband, transmitter systems, and single receiver but wideband, so that it can cater for both the systems in that spanning those 2 bands. something like that. So that puts a kind of demand or requirements for integrated RF systems also. So that is another area where we are working in that area to see that, to combine the systems like. So these are the antenna requirements for that. For example, just to show you what kind of technologies are there around the globe. We had just a kind of study which from the information what is available for us. For example, we looked at F-22, something like it is having 64 antennas, maybe dedicated for each antenna, dedicated for each system, that kind of conventional design. But coming to F-35, which is a stealth aircraft, so the 64 antennas have come down to something like around 20. So they have achieved this one, mostly, putting the shared aperture concept and things like that. That's how the antennas have to be reduced in number. So we're also aiming something like that. So apart when we talk about stealth aircrafts, okay, there are many stealth aircraft existing around the globe. Our stealth aircraft is advanced medium combat aircraft. So that's just to say that is our stealth aircraft. So now coming to quickly look at what are the conventional antennas which already existing on the aircraft today, and how we are going ahead further for new technologies. I'll just give you glimpses of what are these systems and antennas. So so far I'm talking about, now I can show you the actual pictures. This is one radio system, and the antennas generally for the radio system are like this in a conventional design, the blade type of antennas. But our studies, we do the simulations as well as they collect the data from the flight testing and our measurements, things like that. So this kind of antennas pose a lot of drag, and there are of course masking issues and ground plane issues on the aircrafts. So definitely the drag I need to reduce it to the minimum possible level, and remove the masking. So for that we are going for new technologies, and like conformal and shared aperture technologies. And that's how that antenna we have made into a kind of printed antenna, which goes into a fin top as a concealed antenna, so that now it will not pose any drag to the unlike the older antenna size the blade antenna. So that's how the whole antenna takes transformation. This is of course some of the patents, pattern measurements on the aircraft. Because why I was showing that is that what we design antenna and take the pattern measurements in the lab, they will not be valid on the aircraft. Again, aircraft we need to measure it and see how pattern gets distorted because of the aircraft. Aircraft specific things like the surrounding disturbance of the other antennas, also the non-availability of the very good ground plane on the aircraft structural issues, things like that. So that's why we need to measure again once we install the antenna on the aircraft, what is the pattern and how it is. Any distortion is there, things like that. We have to assess it. So this is another C-band system, radio altimetry system. So this antenna, the antenna for the C-band system, and then navigation antennas for the INS GPS system. So you see the INS GPS system, and this is how the navigation antenna looks like. And this is the L-band, and the Vivo ILS antenna, which is the blade antennas we are using so far, and we are going towards the conformal or concealed antennas for this. This is the Vivo ILS system. Then the tactical navigation system, which gives the range and bearing. So that is again kind of blade antenna we are using so far, which we are now making it conformal. And then combined interrogator transponder system, like it is a identification system on the aircraft, which works in association with the radar. So this also has got some blade antennas presently. So we are making it conformal. So so far on the of the antennas like this, which I showed you in the beginning of my presentation also. So this is, the location of the antennas. So closely they are placed, and we need to take care of the interference and other issues while installing on the aircraft. So some of the challenges which we faced while installation and flight testing of these antennas, I'll just as a case studies one or two I just mentioned so that you will get the feel of the kind of problems what we face. For example, interference, as I talking so far, the how the interference affects your performance of the systems. For example, a radio system, we had a lot of interference. The noise, where from it is coming, we don't know, but it is present in the communication system. Obviously, communication system being the important system on the aircraft, on the fighter aircraft, so pilots will not accept that noise. Any type of interference, noise, anything, they won't accept it. It has to be clean and it has to be perfect. So obviously, when we had this noise, where from it is coming, we didn't have idea. And finally, after a lot of kind of investigation and fight, uh, it is coming from a telemetry system. Because generally during the flight testing, we install telemetry systems and their antennas on the aircraft, because the data has to be continuously real time. In the real time, it has to be monitored and it has to be downloaded onto the ground-based systems to collect a lot of information about the flight parameters. So telemetry systems are very important. But unfortunately, in the telemetry system, what we have put it is, of course, it is quite system. So and so the when real rigorous scrutiny was not there, and just it was installed. And so when we suspected this system, telemetry system, the group which has been handling this system, they very confidently said, no, telemetry system is all qualified, well qualified, so it cannot give you any interference, so don't worry about it. So that's how we were suspecting all other systems and all other antennas except this one. So the investigation went on for some time, quite some time. And then finally we had to convince the pilot that you switch off the telemetry system for some time, and then we want to see the interference, because he was not ready to do that, because the telemetry system is of course an important system to transport the data from aircraft to the ground while it is flying. So he was not willing to switch off. So finally, we had to convince with great difficulty. In one sortie, he said, "Okay, I will switch off for a very short period. Then let us see." So he switched off the system, and then obviously interference disappeared. Then that's how pilot also got convinced the telemetry system is giving the this kind of interference. So then again, we have to relocate the antenna and then put it somewhere else, and changes on the aircraft, all that took place. Then finally we reduce the EMI. So that's how the EMI sometimes really gives you a nightmare. The second typical example is masking. When we had these radio antennas on the aircraft, masking became one big issue. Obviously, as like interference, masking also is unbearable, and pilots cannot cannot accept the masking on the aircraft, because masking finally blocks your your voice and data, and it obviously the pilot may not be able to talk to the other pilot and may not be able to talk to the ground station, and which is very important during the flight. He has to be in touch with the ground station. So masking is one big issue on the fighter aircrafts, and which we also faced. And then obviously to remove that, we need to do methodical, survey and characterize the masking, and then how to optimize. So masking 100% we can't avoid because of the constraints on the aircraft. So we need to, but we need to minimize it so that the performance of the aircraft in terms of connectivity will not get affected. So for that, obviously we need to do some adjustments in the system design. I mean, communication system design, as well as the antenna locations, etc. So all that we did, and then okay, we have optimized, but still the masking issues in some of the systems we face, and we are trying to solve it. So like this is what the masking of the top antenna is by introducing conformal antenna and fin tip and things like that. Okay. So the locations, that's how the masking, masking dictates where to keep the antenna, the locations from spine to fin top, and maybe the frontal bottom to or the back side. These things we exercised and tried to optimize that. Then the other issue is when we went for SATCOM link on the aircraft. SATCOM antenna generally comes little bigger antenna. So obviously the bigger antennas give the bigger RCS issues and things like that. So obviously when we have to put the SATCOM antenna, we need to relocate other antennas like VHF antennas and viewer ILS antennas. So that's how we have to again move the antennas from one place to other place like energy door and like that. So then obviously while locating those antennas, we need to look at the mutual coupling issues and other that. So for that we do simulate these antenna performance with the aircraft frame and come out with possible configurations with the existing software tools, and then optimize the antenna locations on the aircraft. So like this. So that's the exercise we go through, and of course during that simulate the patterns and see the distortion and whether the distortion is acceptable or not, whether it is in the acceptable limits or not. All that we have to see, and then analyze. I mean, how to look at these antennas. So the SATCOM antenna installation basically necessitated the fabrication of new parts for spine and relocation of top VHF antennas, and then we went for that, and the locations were again fixed and again simulated, and took the simulated patterns, and then when we put the antennas again, we take the measurements, and then the performance is same. That's how the analysis is done, data analysis. I hope I'm audible and it's okay. Can somebody confirm?
Yes, sir. Yes, sir. Fine.
Good. Thank you. Okay. Now coming back to the again a radiation pattern simulation of these conformal antennas. So with the tools we have, we do these simulations and see that the 3D patterns, how the 3D patterns get affected because of the location of the antennas and surrounding interference due to surrounding antennas. So that is also seen during these pattern simulations. Because if the patterns, if you don't simulate with the at least the close to the aircraft location and the skin available there, otherwise in reality the pattern really gets disturbed like anything. For example, if you see these patterns here, see the kind of distortion. This is omnidirectional pattern for which the antenna was designed. But when I locate it on the aircraft and take the aircraft airframe, the existing things there, the pattern gets distorted like anything. So that's where you need to see that whether this pattern is suffice for your requirements or not, and then otherwise how to improve the pattern or how to improve the installation conditions. All that, it's like back and forth. We do a lot of iterations. Iterations are done. For example, some of the antennas for quite some time we are not able to place because the aircraft designer is not able to give the required location or the required the plane there, etc. And again, some of the challenges we face is sometimes I get very good location, but that is close to engine. So when it is close to engine, even the location is good, but engine temperatures, I mean, that's we need to take into consideration whether my antenna materials will withstand those temperatures, and withstanding those temperatures, whether antenna can perform like what it's supposed to be. So then that is another issue. So these are the issues on the aircraft. Uh, so I mean, we need to take all these into consideration. So another case study for you to just realize the problems is there was some loss of interrogation signal during our analysis for one of the systems IFF transponders. So this is due to polarization mismatch and now continuous switching of top and bottom antenna for the system performance. And then we did study this issue, and the switching based on signal strength was found to be a solution. So that's how we finally optimized the signal strength based on the switching between top and bottom antennas. And the newest scheme was recommended for all these IFF systems. So that is another case study we went through. So those are the antennas for the communication and navigation suits, which I talked about the issues and the case studies. And then coming back to the sensors, like big sensors like radars. So the radars have got, earlier the conventional radars have got this kind of slotted array antennas. The antenna which, I mean, this is a radar which you are seeing, a multi-mode radar on a typical fighter aircraft, is a fire control radar in the X band. And the antenna supposed to move plus minus 60 degrees in azimuth and plus minus 60 degrees in elevation. So it is like, I mean, two directional movement in azimuth and elevation, which is required for the sensor performance. So this kind of conventional antennas earlier are designed with slotted array, and then the slotted arrays, I mean, this is like a plate, antenna plate, which is to be made with technologies like dip brazing technologies. So multiple layers debrazed and made into one antenna. So very, I mean, challenging technology. So we went through the kind of issues in realizing this technology. So once the antenna is made like that, the antenna is put on the servo system for its movement and azimuth and elevation. And this antenna being the very primary sensor antenna, it is installed in the nose cone. So this is a typical radar antenna. This is how it is installed in the nose cone with a servo system. Okay. So, and the as technology progressed in the radars, the antennas, the normal scanning antennas or mechanical scanning antennas become electronic scanning antennas. To look at these electronic scanning antennas with the advent of TR module technology. So this is called AESA radar. AESA radar, active electronic scanning array radar. So this radar, unlike the typical mechanical scanning radar, has got a lot of advantage because of electronic beam steering and the scanning with high speed scanning features. So that's how the radar has got a lot of performance advantages over the conventional mechanical scanning radars. So this is one of the typical indigenous AESA radar antenna designed and being tested on the aircrafts. So this is how the antenna, which has gone through all stages of testing and environmental screening, and then put on the aircraft, installed in the aircraft, and being tested now. And if you see, this is the TR module which is designed for this kind of antennas, AESA radar antennas, in big numbers. Something like a typical is some 1,000 TR modules exist for this antennas. So that's how the antennas are designed. And obviously this slide what I'm showing is when we design these antennas and systems, we integrate on the ground, test it on the ground rigs, and then take it on the aircrafts. So I'm just showing some of the ground rigs which we establish for the quite good ground testing before taking out of the aircrafts. So this is of course the radar rigs and avionics rigs. which we use for testing. So that is about the radar antennas. And of course, radar antennas, as I told you, a lot of design challenges and technological developmental challenges exist there. And some of things I have, just brought out, like debracing technologies and things like that. So that is one thing. The second important sensors on the aircraft is electronic warfare systems. So we have a typical electronic warfare system on the aircraft and in terms of receiver warner, and jammer, and high power jammers. So this is a typical EW system with the warning, part of it, which is RWR, radar warning receiver, with up down antennas and high definition antennas. Then jamming part of it is with transmitting antennas. You see the here the number of antennas is high. Typically something like a dozen antennas will have. This system will have a dozen antennas, something like 6 on the warning side, and then some 6 on jamming side. So the system has got features for electronic, threat warning, and then obviously to take care of the sources which jam your radars on the platform. So that's how the system works. And this is typically a wideband system, which spans from up to something like 18 GC. Okay, starting from 1 GC. So we need broadband antennas for this kind of systems. So this is a typical radar warning receiver. Of course, we are calling it next generation receiver because it is a digital receiver with all advanced features. So this system has got CBS antennas, typical number something 4 to 6 CBS antennas. And then the jammer arrays will have the antennas with array type of antennas. If you see the typical array for jammer, and of course this does the receiving part also, receiving and jamming both it does, and with typical TR modules. These are other same arrays, 32 array antenna, 16 array antenna in various configurations for this EW system. You see that, and this is another antenna array, which is bullet antenna array, we call it. So this is also designed for a EW system, 16 element or 32 element kind of thing. This is a 32 element bullet type of array. And of course, the other circuitry around the array, which you are seeing here, we call active array TX RX unit for a EW system. So that is being tested on the aircraft. So basically, for the integrated or unified EW systems, the antenna locations you see here, there are a number of antennas come on that. Some of the antennas on the wing tips, some of the antennas on the fin tip, and some antennas on the wing roots, and some antennas on the spine, like that. So many locations we need to keep them and make them perform. And there are of course jammer pods. For some of the jamming operations we use pods, and the pods also will have jamming antennas at the tips of front and rear tips of the pods. So the jamming antennas we need to employ there. So that is how. Then these pods are installed on the aircraft like this, and here also we face a lot of masking issues, because when the pod is installed either at the, let's say, outboard or midboard, or inboard stations, what happens is, because of other weapons nearby, other weapons and missiles nearby, the masking issue comes up for the jamming antennas. So that is one thing we need to address while keeping the jamming parts and the antennas and the jamming parts. Of course, we don't have much choice there, but still, obviously, the system performance we need to take care of. So hence we do take the considerations into account before final designs of these jamming antennas. And these are high power jamming antennas. So hence the masking and reflection issues, interferences we need to worry about depending on the pod's location. The typical outboard locations of the pods don't give much issue, but when pod is coming inside, that is midboard or inboard locations or central locations, then obviously the masking is very high due to the drop tanks nearby that pod and other missiles and weapons nearby the pod. So those things, I mean, we look at it and carefully, I mean, design the antennas. So now, because we, I mean, for the advanced aircraft designs, we are moving from conventional antenna design to the conformer or concealed antennas. So I just summarize. As I told you, these are the conventional designs of the antennas and for the systems in the various bands, like VHF band marker antennas, VRLS antenna in the VHF band, communication antenna VHF band. These are the antennas I have shown you. And again, SATCOM antenna for the SDR, and then TACON antenna L band, IFF and L band, GPS in L band, again SATCOM in L band. And these are the, I mean, the antennas which are in the conventional design form. And we need to move towards now the advanced antenna designs from the conventional designs. This is, of course, RW antenna in the wideband. This is the jamming antenna, the conventional type. And these are the conventional radars. If you see the conventional radar, the typical radar in X band has got this kind of antennas. And now we are moving towards ASA radar antenna of this kind. So these antennas we move to advanced designs, how they take the shape. For example, a VRLS antenna in the VHF band in the conventional form has got typical blade type and all that. It becomes concealed in the nose cone just below the radar antenna, and it becomes like a skin of this nose cone radome, and concealed that. So that's how the new technology or the advanced technology makes the antenna like this, concealed and conformal. So that's how the technology development is progressing now for the advanced fighter aircrafts. The communication antenna, which is blade antenna, a typical blade antenna in the conventional design, becomes concealed in the fin top like this, just to show you how the technology transforms these antennas. And then same way, the communication bottom antenna becomes conformal concealed at that place like this. And the UHF antenna, UHF SATCOM antenna for SDR, so software defined radio application, becomes conformal concealed in this shape. Then the TACON, IFF and data link antennas become conformal concealed at their respective positions from the earlier conventional designs for the advanced fighter aircrafts. Then the RAM antennas become conformal like this, and GPS antennas become conformal in this form. So this is to show you how the technology changes these antennas. And as I already told you that conventional radar antennas become ASA radar antennas, of course, because there the TR modules are there, and TR modules with each TR module has got an antenna element. They become an array of this nature in the X band. And then obviously the RWR CBS antennas become concealed at the wingtips, and the jamming antennas become arrays at wing roots, things like that. And so these are the whole overall picture I have shown you, how the conventional antenna design become the advanced antenna design for the advanced aircrafts. So this is a kind of the views top and bottom of a advanced stealth aircraft, and the locations of the antennas I'm showing here, how they are located at different places in the aircraft. So this is a typical layout of the antenna locations on the aircraft so that the systems meet the performance. One is RF and micro systems, they have to meet their performance with those antennas, and obviously not undermining the performance of the aircraft for its stealth and other characteristics. So those two have to coexist on the platform, so that not interfering with each other's performance, rather enhancing each other's performance. So these are the other typical antenna locations and studies for these aircrafts. And you see some of the antennas we need to keep on the rear side of the aircraft and close to engine bay. And there, as I told you, the typical issues of the engine heat and engine flame, and then the antenna has to withstand that temperatures, still perform, and also the maintenance. It should not pose the maintenance issues again due to these engine flame and engine temperatures. So those issues we need to take care of in the maintenance also, because the aircraft again I have designed and say, let's say I say developed the aircraft, but unless I know design such a way that maintenance is easy for all these systems, including the antennas. Otherwise, then again, the aircraft is not accepted by the squadrons. So they look at the maintenance aspects also, while systems are getting developed and being installed on the aircraft. They look at the maintenance issues. They say that okay, this antenna which is close to typically, I'm giving an example, which is close to engine and getting exposed to engine temperatures. So do you need to change the antenna every now and then? Every 6 months, I change the antenna, because antenna performance should not change after some time because of the temperature affecting the material of the antenna or the radome, etc. So those are the aspects. The maintenance people look at it from the squadrons, and they say that no, this maintenance cycle is not acceptable to us. So you need to design the antennas with good materials. So things like that, because the aircraft people may not be aware of the issues with antennas. They typically say, why don't you make your antenna smaller? I mean, this is one thing which we face very frequently with the aircraft designers. Of course, I don't blame them, because okay, from their perspective, they say, why do you bring such big antenna? Can you make it small, little small? Can you make it conformal? Why do you bring such big structure here? So like that they talk, but we know that there is a physics and engineering which beyond which we cannot compromise and make antenna smaller or conformal, things just like that. Not possible. So we try to convince them so that it's not possible. You need to take this structure and install it wherever it is. So like that, we keep going back and forth with iterations and things like that. So really, it's a great challenge, and of course the great opportunity also to perform there. So that's how these antennas are located. Now quickly we talk about some of the antennas systems where for the stealth aircraft, how important the radomes and low observable structures. Very quickly, I'll just go through that. Basically, works like a bandpass filter. Suppose if the system like radar is in the X band, and from the stealth point of view, I have to reduce my RCS. So I need to design FSS radome for this sensor. In that X band where the radar is working, the radome is open, transparent, but all other bands, it is opaque. It is, it poses high loss. So that kind of radomes are the present technology. Of course, the next topic is on the, by Mr. Dr. Shivanarayana from NL is on this topic, and he will talk more elaborately. In fact, he is designing one FSS radome for us also. So he will talk about it. I'll just give you the glimpses of what kind of radomes exist on the aircraft for radar antennas. This is a typical nose cone radome, quartz radome. This is I mean, the state-of-the-art technology, Kvarj radars. So, because a typical radar, fire control radar on the stealth aircraft, uh, I So that calls for FSS Radomes in this area, and that's how the aircraft requirements for stealth and based on the material bulk integration on the aircraft and installation on the antenna, and with other things like air data probes, the loads and lighting. So these are the aircraft side requirements, and I need to meet to the aircraft requirements with the antenna as well as the radome from the point of view of the available volume and the bandwidth, transmission efficiency, side lobe degradation, and bore sight errors, which is again another important while designing the radome for a antenna. The bore sight errors I need to take care of, and the lightning productions. So from these typical requirements point of view, an advanced aircraft like a stealth aircraft will have the radomes of typical shapes. You see the shape of the radome from the point of view of this RCS consultations, things like that, and other aircraft performance. So the spacing distance between structures and viewer ILS antenna, of course here because I'm putting a viewer ILS concealed antenna, conformal antenna inside the same nose cone antenna. So nose cone antenna along with that, it coexists in the same radome. So that's how I'm showing here in this slide. The shapes of these radomes are again another challenge for realization, which probably my next speaker will talk about it. And this is a typical installation diagram of these radar antennas along with the radome on the aircraft. Of course, just to give you how a very advanced radome of F-35 looks like. This is, as we understand, this is an FSS radome for FM and F-35. And we also attempting now and going ahead with this kind of radomes. A typical radome, of course, designed and developed by NIL for FSS applications is this radome. And Mr. Shivaran will talk about the design aspects of that. And apart from radome, we do design some of the low observable structures around these sensor antennas like radar. So that also we are doing now. So this is to reduce the RCS of these structures, including the antennas. These are the typical, bulkhead structures, which we keep it around the antennas in the nose cone. So just to look, see that if you look at this, sorry, yeah, this is the fourth generation aircraft slide in which the bulkheads are, the shapes of the bulkheads are designed typically like this. The bulkhead design also plays important role to reduce the RCS of the aircraft, and the bulkheads, how they get shaped or changed in the fifth generation aircrafts. Why I'm talking about bulkheads is because the bulkheads the design again have an impact on the design of the radar antennas, the AESA radar antennas. You see the AESA radar antennas, how the shape share got transformed due to the bulkhead design, and the bulkhead design because of the RCS considerations. So that's how the shapes of the antennas got changed. And if you look at the nose cone radome, FSS nose cone radome, the requirements of that for the stealth aircraft, it shall provide frontal aspect out of band RCS reduction, the radome, and it shall have maximum in-band transmission and symmetrical and ogive shaped radomes. So challenges are really, these are the challenges, technological challenges, because of the asymmetric shape, lightning protection, and then other band IFF band integrations. So And there's another thing from the RCS engineers that if you design the antenna with this kind of shape, not the circular shape, the RCS will be less. So again, you have a challenge from the circular shape to this kind of mosaic shape for antennas, especially in the radar antennas. So that is another challenge for the design challenge for the antenna designer. So now I have come to almost the end of my presentation. So I'll just summarize what I talked about for last 1 hour. If you see that the antenna design and development for fighters and especially stealth aircrafts is a big challenge. And the people who are in this field, they know the challenges. Obviously, the challenges arise due to space and volume constraints on the aircrafts because of limited locations and coverage requirements, masking issues, and limitations due to aircraft structures like wings, fuel tanks, and load-bearing members. So the design constraints due to wideband requirements for EW antennas and omnidirectional coverage issues for the design is very stringent in VHF and lower frequency. And then in addition to the space and volume constraints, we have RCS low profile constraints for good minimum size and weight, and then coverage issues. Then other constraint is the drag, which I explained you. The drag performance of the aircraft cannot be compromised, and hence I need to reduce the size of the antennas. Then, of course, environmental stringent antennas like shocks and high temperatures and low temperatures. So that's how the environmental. Then obviously we have wideband coverage requirements for the some of the systems. So with all these design design constraints, or I say design requirements, I don't say constraints. It's a requirement, and I need to meet the requirement, and there is to make it as an opportunity. So with this, the new technologies which have come for the design of these antennas for the fighter aircrafts is like multi-band shared aperture antennas have come now. FSS is are available now, and then conformal technologies. We call it next generation conformal technologies for the elements of multiple systems with mutual coupling effects, high power handling issues, and wideband coverages. So we need to employ the conformal technologies. That's how the aircraft is designed. And so this slide is to show you how the aircraft performs in one of the exercise like Gagan Shakti of the Indian Air Force. And I mean these systems and RF and microwave systems with their antennas play a very important role in the and the power of these aircrafts, performance of these aircrafts. So with that, I come to the end of my talk, and I really thank the organizers of this workshop, Dr. Chenmai and Dr. Karthikeyan and others, and obviously the most important person for me, the inspiring person for me to talk on this antenna subject, even though I'm not antenna expert, is Dr. Sudhakar Rao. He has been really encouraging me and inspiring me and to work in this area, as well as convey my experiences with you. So I really grateful to Dr. Sudhakar Rao and organizers of this talk, and of course a big thank you for all your time and patience, the online audience now. So thank you so much, and Jai Hind. And now, if you have any questions, I will address for 5 minutes before the next speaker starts. Thank you. So over to Chinmay and Karthikeyan.
Sir, thank you very much, sir, for your interesting and inspiring talk. You started with the basics of fighter aircraft and discussed about the requirement of combat aircraft, features of the modern radar systems, and also the requirements of conformal radar. I think so. since we have limited time, we will take up one or two
Yeah,
questions from the
sure, sure,
audience.
sure. Yeah.
So the first question from Shreya Gosal: how to reconfigure the antennas so that it can distinguish between friend and enemy aircraft, specifically when multiple nations are involved?
Yeah. Basically, uh, to identify friend aircraft or the enemy aircraft, the antennas are not the typical things. There are systems on the aircraft which communication and as I told you, the identification systems on the aircraft. So they work obviously for identifying an aircraft as a friend or foe. Typically, in an IFF system, identifying friend or foe system works in association with the radar. And when radar detects a target, they transmit a typical secret code towards that target. And if the target is friend, of course, the friend knows my secret code or password, and he replies. Uh, so I know that he's a friend. If he is not doing that, he is my enemy. So your question is very right, because before I attack the target, that means basically releasing a missile or a weapon to the target. I need to confirm this whether he is my friend or foe. So that um,
Yeah.
further and
Yeah, thank you,
uh,
sir. Hope.
yeah, yeah. Yes, Karthikeyan. I hope I
Yeah,
addressed.
thank you, sir. Hope the participant doubt got clear. We'll move on to the next question. Uh,
Okay.
Please comment on radar two-way array factor and how this transmit aperture and receive aperture sharing same aperture.
No, we don't. See, the aperture is the same for the radar, for the transmission as well as reception, but the beam patterns will be little, slightly different for the transmit beam and the receive beam, depending on the requirements of the radar. So the aperture, obviously, I need to have to design a single antenna for the transmission and reception with the the same aperture.
Okay.
But while transmission, I apply the transmission pattern, and while receiving the receive pattern, I apply, and that is typically a software programmed values. We do that for the pattern, pattern shape, pattern tapering, and then getting the pages in that games and all that. So that's how it is designed. Okay.
Yeah, thank you, sir.
Yeah.
A question from Dr. Malay Ranjan Tripathi. Can we use AFSR and AFST structure with the low RCS antenna in the radome?
What is a AFSR structure? Can you ask him what is it?
Uh, yeah, Dr. Malay,
Dr.
Malay
Malay?
Ranjan, are you
I
there?
know Dr. I know Dr. Malay. Okay.
Okay.
Yeah.
Okay, sir. Shivada, can you
Sir,
unmute him?
sir, good morning.
Yeah. Good morning, Dr. Malay. How are you?
I'm fine. I'm fine.
How are you? Yeah. Yeah.
So
Please.
actually,
Please.
yeah, I was interested to talk to you, and that's why I asked the question.
Sure. Sure. What is that AFS structure?
Sir, this is the we are working. This is the new structures. I work with the Professor Rajmitra.
Okay.
This is actually objective frequency selective surface,
Okay.
uh, reflector and transmitter. So
Okay.
we can use this thing, and we can also use in hybrid also both the things,
Okay.
and we can have the low band absorption and the higher band absorption, and in between we can have a transmitter
Yeah.
with a low RCS, so that we
Okay.
can increase the aperture, and also we can also
Yeah,
uh,
you can use
have a,
these structures for FSS
yeah,
Radomes,
yeah,
but basically, okay, FSS Radomes, when you design, depending on which antenna you're designing, that antenna bandwidth requirements and that system requirements you have to meet. If you can meet that, these structures can be used.
Yeah. We
And
are working
obviously, other thing is environmental requirements, like whether it's the structure should withstand the
yeah,
temperatures and vibration requirements.
temperature and
If
all.
they can, yeah, if they can meet, yes, definitely you can use it. Okay.
Okay, sir. Thank
So
you.
yeah,
Nice to see
yeah.
you. And
Thank
you
you,
have given
Malay.
inspiring
Nice to see
lecture.
you.
Yeah, sir.
Yeah,
Yeah,
thank
I
you.
ask question because I want to talk to you. Yeah.
Definitely.
Okay.
No, no, you can even call me separately also and talk to you. No problem. Yeah, please.
Thank you. You are
Thank you.
looking fine. Okay, sir.
Yeah, sure.
Thank
Thank you.
you.
Nice talking to you,
Okay.
doctor.
Yeah.
Yeah,
Yeah,
thank
thank
you.
you, Dr. Malay Ranjan. Sir, one more question, probably we can take it from the audience.
Sure.
Actually, time is nearing for the next session.
Yeah.
Sir, if the size of the Vivaldi array shall be reduced, can we
Mhm.
use LTCC technique that promises comparatively less size?
Yeah.
The question from
L
Sandana Mahalingi.
Exactly. LTCC technology we are using for the radar antenna arrays rather. That's of course the good technology, LTCC technology. That's basically comes with embedded or integrated with the kind of TR modules when we design for the AAC radar antennas. Yeah, you can use it for Vivaldi arrays also. Um, so yes, you can employ and I have seen some LTCC technologies also which are being used for the radars. So you can use it. Yes, answer is
Yeah, thank
affirmative.
you, sir.
Yeah.
Sir, thank you, sir. One last suggestion from Sudhakar Rao, sir.
Uh-huh.
Can you give some guidance to students to
Mhm.
get acquainted with aircraft antennas? Any textbooks or papers you please share?
Okay, definitely. I'll share with you probably with you and Chenmai. I will list out and I'll send it to you and mail to your email. Okay, I'll share definitely. There are good books are there for the aircraft
Yes, sir.
systems and the antennas. I
Yeah.
will share with information. Sure.
Yeah, thank you, sir. So,
Thank you. Yeah.
sir, with this, we can just wind up the session.
Yeah.
So, dear
Thank you.
participant, still you have a questions, probably you can contact NNSRK, Dr. Prasad, sir. So, probably he can answer through mail. And also about the books and some papers related to aircraft technology. So, probably sir will share with Dr. Chinmayi, and probably from the organizer you can get it. So thank you very much, sir, for your inspiring and informative
Yeah.
talk. So
Yeah.
probably sometime later, so once the